In this video, we'll learn about angular frequency and the defining equation of simple harmonic motion. We'll start with angular frequency, and then we'll move on to the defining equation of simple harmonic motion. We've already learned about angular speed or angular velocity in subtopic 8.2 when exploring circular motion. Now we'll make a connection between simple harmonic motion and circular motion. To do this, we'll compare the motion of a simple pendulum with the motion of an object that is moving on a circular path. For both the oscillating pendulum and the object moving in a circle, we have the time period of the motion. For the pendulum, it is the time it takes for the pendulum bob to complete one full oscillation. For the object moving in the circle, it is the time taken to complete one full revolution. Let's assume that the time period of the pendulum is the same as the time period of the object, and denote this time period using the letter t. For circular motion, we denoted angular speed or angular velocity using the lowercase Greek letter omega. We defined angular speed as the angle around the full circle, so 2 pi, divided by the time period. Even though in simple harmonic motion, the given object is not moving on a circular path, we denote angular frequency using omega and define angular frequency as 2 pi over t. The unit of angular frequency is 1 over second, which is the same as the hertz, hence the name angular frequency. Also, it would not make much sense to call this quantity angular speed for simple harmonic motion, because an object oscillating with simple harmonic motion does not move at a constant speed. These are the formulae that relate angular frequency with the time period and with frequency, and these are the variables in these formulae. Now that we have learned about angular frequency, let's move on to the defining equation of simple harmonic motion. In the video about simple harmonic motion, we learned that the acceleration of an object oscillating with simple harmonic motion is proportional and opposite to the displacement. We express this relationship as a, so acceleration, equals negative k times x. Here k is a constant, x is displacement, and the negative sign shows that the acceleration and the displacement are always in opposite directions. Now, to make sure that one side of this equation is always positive and the other side is always negative, we can slightly modify this formula and write that the acceleration is equal to negative a constant squared multiplied by the displacement. Squaring the constant ensures that we always get a positive value. Finally, this leads to the defining equation of simple harmonic motion, where a is acceleration, omega is angular frequency, and x is displacement. This conclusion completes our learning about angular frequency and the defining equation of simple harmonic motion.